So the last sub-op that we're going to cover is the case cementing sub-op. If we go to the 9 5/8 cementing sub-operation, it takes us to this screen. Now these plots immediately look different than the other sub-ops that we reviewed because we're plotting loads versus volume displaced. At least on the driller's view plots, that's what we're doing. So as the cement job is displaced, that's shown on the x-axis, and then on the y-axis is a given load. So here's our surface hook load, our surface torque, the ECD at the bottom of the casing, and then the pump pressure at surface. Now there's a variety of different things that have to be manipulated in order to create the plots that we typically want to see. So for example, if I was planning on rotating this casing, I would have to go to the effort of putting in a rotary speed. Let's say that I'm going to rotate this casing at 30 RPM during the cement job. So if I type in 30, immediately on the torque graph, some torque curves will appear. And what this is showing me is the surface torque at the start of the cement job, the middle of the cement job, and towards the end of the cement job. One of the features that's really fun to play with is dragging the fluids around the wellbore so that you can visualize where everything is as you start to analyze this response. So we'll just blow this curve up a little bit. Here's my plot of my surface torque during the cement job. Now over on the wellbore, you can grab the trailing edge of the cement. You can actually pull it up the hole, and a marker will appear on the graph that shows the position of the slurry throughout the job. We can drag this up to the very beginning of the job as the spacer first enters the hole, as the lead slurry enters the hole, as the tail slurry enters the hole. Of course, it makes its way down the wellbore, entering into the high angle part of the casing, and eventually at this point it starts going out in the open hole. And that's where we start to see a separation of the different torque friction factor curves, because this plot is a sensitivity to cement friction factor. We've got a friction factor for cement, we've got a friction factor for the mud itself. In cementing, we can't actually do a sensitivity to mud. We would do that in our tripping sub-op. In the cementing sub-op, the only friction factor sensitivity we can perform is that for the cement itself. So for a range of different friction factors, this is what the surface torque will be as the cement is placed in the well. So kind of fun. If we go back to 4-plot view, that's if I wanted to make a torque plot while rotating the casing. Maybe I'm not going to rotate the casing. Maybe what I'm going to do is reciprocate the casing. So I'll put 0 RPM in and say that I'm going to reciprocate the casing at 50 feet per minute. Well, now on my hook load plot, what will appear is my rotating or neutral hook load at surface during the job, slack off, and pickup hook load. And you'll notice, depending on the friction factor, I might actually get into a condition of negative weight when I'm slacking off, or I could even potentially get into a point where I can't pick the casing up, just depending on what my hoisting limit is and what my friction factors are. So that's also kind of a fun thing to analyze as you drag the string around the wellbore. What is it that's actually happening in the well? That plot, or these two plots, are also very interesting to view in a snapshot mode. So if we click on snapshot, go to a 2-plot mode, and drag the fluids around the wellbore, you can see how the curves kind of evolve. If we lock the axis, makes it a little bit easier to maintain our perspective. We can see how the tension or compression starts to develop throughout the string. Likewise, when we're rotating but not reciprocating, unlock the axis here, and then we'll just drag the string up the hole. Yeah, things change as the fluids move. Kind of a neat thing to be able to visualize. We go to a 4-plot mode. We could also rearrange the plots and look at the side forces right next to the tension and the torque, if that's what we're interested in. As we drag the fluids around, sure enough, side forces change. It's also pretty neat to be able to see. You could even see how the standoff changes. I'll unlock this, come over here and look at our relative standoff as the fluids move around. So we'd like to be closer to 60, 70, 80% standoff. Let's see where we're actually at. But yeah, the standoff changes when the fluids are inside or outside of the pipe, since the side forces also are changing. Turns out standoff's a little bit better when the cement's on the backside due to the buoyancy effect. This would also be a good opportunity to evaluate the effectiveness of centralizers. If I click on the string builder, I could go to the add accessory box, pull down a rigid centralizer, find one that's good for 9 5/8. Here's a 9 5/8 rigid centralizer. We'll just drag that onto the string. Oh, looks like a small one. We'll try a little bigger one. That one might be small too. Let's see. Outside diameter. Well, we want a bigger one. Let's say we're going to go with a 12-inch diameter centralizer. We'll drag that up the well, and sure enough, look at there. Look what our standoff is. If I'm scared about a 12-inch centralizer, I could easily try different diameters until I find one that gives me the standoff I'm looking for. So there we go. One 11.5-inch rigid centralizer per joint gives me pretty reasonable standoff. Just one way to use that. What else do we want to look at here? If we go to driller's view, come back to that. And now we're going to look at sensitivity to flow rate. We're going to turn off the rotary. We're going to say we're not rotating, we're not reciprocating. We're just going to pump this job. If I click on the flow rate box, that will show me the ECD at the bottom of the hole as the job is pumped, sensitivity to flow rate. And here we see that the ECD really climbs fast after about 1,200 barrels are pumped. If it doesn't make sense why that's happening, we could investigate it by, again, dragging the fluids around, seeing where the fluids are. Sure enough, right at this moment, that's when the cement starts going into the annulus because the cement's heavy and thick. The ESD and the ECD start to increase. The other way of viewing this is on the snapshot plot. Come on over and rearrange my plots so that I've got my ECD, friction pressure, total pressure. All right, they're all together. I just need to scroll over here to the right. Yeah, and we'll just look at 3 of these here. How about 2 of them? Yeah, and we'll show friction pressure when I'm just rotating off bottom. I'm looking at apples and apples here. If I lock the axis and pull up the cement, I can actually see a snapshot of the ECD and friction pressure in the hole during the entire job, which is pretty neat. You can see where we're breaking down, when we're breaking down. In case the weak point doesn't happen to be the bottom of the hole, if it's somewhere up hole, that's much easier to see on the snapshot view. Unlock that. Come back to driller's view. 4 plots. Okay. Pump pressure, that's pretty self-explanatory. Gauge view. If I was rotating a liner, let's say. In fact, let's just go to where I do have a liner. Go back to the home screen. 7-inch liner, cementing. If I'm concerned about the torque that's felt at the liner top, a good way to analyze that is on the gauge view. And I'll come down here and say that my gauge is located at a depth of 16,500 feet. Now these plots will show me the load at that 16,500 foot point. That's where my liner top is. This is the torque load, the ECD, side force, etc., felt at that particular point throughout the entire job. Pretty interesting way to view the loads. Fluid schedule. If I click on fluid schedule, that's going to pull up a description of what it is that I'm pumping. I've got a little schematic on the left of the string in the hole and where the fluids are. If I want to add a fluid to what's been assumed by default, I can click on this fluid box and then drag it over to the interface of where it fits in the schedule. If I wanted to pump something ahead of this, ahead of my spacer, I would put it at the top of the stack. Say I'm going to pump base oil. Pumps 50 barrels of base oil. Base oil is not cement. Click OK, and now I've got base oil ahead of my spacer. Then, of course, we can just rearrange these fluids. If they're not where they belong, we can click on them, pull them down, and now they're in a different position. There's some tips up here. If you change your top of cement, if you want to move your top of cement to a different depth, let's just say we're only trying to get top of cement to 18,000 feet, and this will do some calculations for you and tell you that you need 25 barrels to get to the top of cement. Right now we have 51 barrels too many, so we need to remove some cement. Maybe I don't want my intermediate lead slurry, so I'll take this slurry and delete it with a right click. Now I just have tail, and it looks like that is the perfect amount of tail to have to get the top cement to that depth. So that is how I edit my fluids. If I wanted to change the rheological properties, I can click on this edit box and it'll pull up a library full of cementing fluids. And just by clicking on one of them, it'll show me my different rheological characteristics. As soon as I click OK, those changes will be saved. Those are some of the features in the Trip Cementing Subop.